So we know that those reactions that we've done before are reversible. Yep. We've shown that. We've shown that if we take a standard ketone, we add our nucleophile, that gives us O minus, and then what we've said is that we can then, obviously, we could have that go back the other way. Yeah? And we can reform our carbonyl. So that's, you know, we've said it's reversible and we can do that. So what happens if we have another leaving group present? Okay, so if we have another leaving group present, we can do the same thing. Look, we start by drawing our arrow in. So we attack our nucleophile, attacks our carbonyl carbon. We then break the carbon-oxygen double bond. Then we end up with this tetrahedral species, which we've had all along. But if L is a good leaving group, then instead of the reverse reaction involving the nucleophile leaving, maybe it involves the leaving group leaving. And so what we would effectively do is substitute the leaving group for the nucleophile. So it becomes a form of nucleophilic substitution. Okay. So our nucleophile attacks, so we have this tetrahedral species, and then it has a choice. You know, we could protonate the oxygen, okay? We could just have the nucleophile leave again, or we can have the leaving group leave. And depending on which one of those it does, you will end up with a different product. But what we're going to talk about now is the fact that if you have the leaving group leave, you get a substitution rather than an addition. But we're going to have to be really careful about the mechanism we use for this. Because although we're saying it's a nucleophilic substitution, it is not an SN1 or an SN2 reaction. So let's have a look at what we mean by that. It's an addition followed by an elimination. So we'll look at that in a little bit more detail. Okay, so what it should look like is this. We have our carbonyl with our leaving group. We have our nucleophile. Okay. Our nucleophile is going to attack the carbonyl carbon. So that's the addition step. We're going to break the carbon-oxygen double bond. Okay. We've then formed our tetrahedral intermediate. And then from this step, we're going to reform our carbon-oxygen double bond, and we're going to make the leaving group leave. And we end up with our nucleophile has now substituted for the leaving group. Okay, so that is the addition. So the first step is the addition. The second step is the elimination. So that's what I want to see. That's full marks. Okay. What I don't want to see is this. So we take our nucleophile, okay, and we attack our carbonyl carbon, and we're saying, oh, it's a nucleophilic substitution. It's SN2 style, isn't it? So the nucleophile attacks, and at the same time, the leaving group leaves. And that would give us that. Okay, that is wrong. And why is it wrong? Because as I've said all along, once you have that choice, once you add the nucleophile to that carbonyl carbon, what's more likely? That the weaker double bond is going to break, or the strong sigma bond is going to break. Okay, so we're going to always break that double bond first. So although you might think nucleophilic substitution, oh, that means it's got to be an SN1, SN2 reaction mechanism. No, in this instance, it's an addition followed by an elimination. And the same thing applies that what you wouldn't do is have the leaving group leave first to give you this kind of weird carbocation, and then have the nucleophile attack that. Because again, this species here, although there is some stabilisation from the oxygen, it wouldn't be particularly stable. When we were doing it in the aromatic chemistry, in that Friedel-Crafts reaction, okay, there was some additional stabilisation to that, but there isn't in this instance. Okay, so this one again would be wrong. What you might see when you look through various textbooks or when you're looking at other examples of this somewhere else is you can see what's called a shorthand style, which is where the nucleophile comes in and attacks just like all the other times. We then break the carbon-oxygen double bond, but we recognise that the very next step, what are we going to do? We're going to reform that carbon-oxygen double bond. So often you will see it drawn like that. You'll see it as two arrows saying first it goes one way, then it goes the other, and then the leaving group can leave. Okay, so the top one is okay, the bottom one is okay, but the middle one will make me cry, okay? Because that's the one where I said, you always break that double bond. And I've said it enough times now that I'm hoping it's sunk in. I know it will obviously be the person who's not here, because they haven't heard me say it 1,000 times, that won't do that. But please break the double bond first, okay? Really important. And remember, although we call it a substitution, it really is an addition followed by an elimination. Okay, but how do we know this is going to happen? How do we know when it's going to happen? It's all going to be about the leaving group itself. It's the nature of the leaving group that is so important. Okay, so on the next page, the leaving group is the absolutely crucial thing. So when we look at, for example, the aldehydes and ketones that we've been looking at so far all along, what do we think? Well, the leaving group of an aldehyde would be H-. And I've told you this morning, H- doesn't exist as a species in its own right. And that's why I'm being really important to tell you it's because of the metal complex hydride that you get H- attacking. It isn't truly H-. So what I don't want to see is you thinking, well, I can have H- as a leaving group because H- exists. It doesn't. So H- is a really bad leaving group. And the same with R-. R- is not a very good leaving group. When you start to look at this, you'll understand, you'll look at things like the pKa value. How easy is it for, RH to lose a proton to form R-? And what we know is it's really not easy for that to happen. If you think if hydrocarbons are full of carbon-hydrogen bonds, they don't spontaneously lose hydrogens. Okay, so R- as a leaving group is just not stable at all. When you go to things like acid chlorides or acyl halides, okay, where you've got a chlorine on your carbonyl, Cl- is a fantastic leaving group, and we know that it's a fantastic leaving group. So, because we know that if you think of the acid HCl exists as H+ and Cl-. So we know that Cl- is a very good leaving group. And when we look at the carboxylic acids, and we've kind of done this when we were doing the acetal formation and the imine work, H2O, especially if we've protonated it within our reaction mixture, is a really good leaving group. So having this is a really good leaving group. So the nature of the leaving group is what will determine whether it follows this addition followed by an elimination. Okay, so that's the most important thing. So if we then look on the next one, we've given you a nice table. Okay, so this is what will help you to understand that if you have these kinds of carbonyl groups on here, so this is your carbonyl compound, reactive ones with good leaving groups are acyl halides, thioacids, thioesters, because the leaving group, these leaving groups are pretty good leaving groups. You've then got the moderately reactive one, okay, and that's where you've got a good leaving group, but it requires some kind of activation. It requires, for example, protonation. So then these ones will be reasonably reactive, but then what we're saying is for this kind of addition and elimination, aldehydes and ketones are really not good. Okay, so that table is really useful for you to get an idea of what makes a good leaving group and what doesn't.